Hi students, now I am going to explain you about one of the important topics in organic chemistry, that is about electron migration effects. The first one is about inductive effect. Okay, what is inductive effect? It is generation of polarity in a sigma bond that is caused by the polarization of adjacent sigma bond. Let us see. Okay, the carbon atom bonded to halogen, which in turn bonded to another carbon. Like that, here we can see the 3 carbon atoms. Okay. Now, the bonds are shown in terms of electron pairs. Halogen, being more electronegative, is attracting the electron pair. As a consequence, partial positive charge on carbon, partial negative charge on halogen is developed. Now, to nullify the partial positive charge, carbon would attract bonded pair of electrons between C2 and C1 towards its side. Okay? So, now you can see the movement of electrons towards C1, thereby C2 develops little amount of partial positive charge. The process repeats. Again, C2 is attracting the bonded pair of electron between C3 and C2. So, C3 also develops little amount of partial positive charge. So, the polarity developed in adjacent sigma bonds due to the polarization of electrons between one sigma bond, adjacent sigma bond, that is called as the inductive effect. Okay. Now, you can see here the order, there are two types of effects, that is, one is minus I effect, where the electrons are pulled by the certain groups, and the other one is plus I effect, where the electrons are given. Okay. So, now these are the different groups which will withdraw the electron. So, this is the order of withdrawing tendency of different groups. Okay. So, you should remember this, practice this, because in the examination they will ask you, may not be all, they will keep 3 or 4 groups, and they may ask you which is the correct order of increasing tendency of minus I effect of different groups, increasing tendency or decreasing tendency, like that they can pose in any way. So, you need to remember this order. Okay. Now, there is another order here, that is, if the electronegativity is decreasing, then the tendency to attract electrons also decreases. You know that fluorine is most electronegative, therefore, it is highly electron withdrawing, followed by chlorine, next bromine, next iodine. So, this is having highest tendency to withdraw the electron. Similarly, here also fluorine has got highest tendency, next is oxygen, next nitrogen, and of course carbon is the least. So, this is also order of fluorine, hydroxy group, amino group, and methyl group. Okay. Now, see here we are comparing the electron donating tendency, that is plus I effect of different alkyl groups. Here you can observe tertiary butyl group being the highest. This is more than isopropyl, which is more than ethyl, and that is more than methyl. Okay, which is more than methyl. Like this, tertiary butyl group has got highest tendency to give the electrons by the plus I effect. Okay. Now, here there are different applications of inductive effect. One is related to the reactivity of alkyl halides. Now, if you observe here in this particular slide, this is a tertiary butyl halide. Now, when this gets ionized, you get a tertiary butyl carbocation, which is being stabilized by the plus I effect of 3 methyl groups. Therefore, this is highly reactive. If you observe the isopropyl halide, the plus I effect is only due to the 2 methyl groups. Therefore, this is little less reactive. Coming to ethyl halide, here when a carbocation is generated, this is stabilized by the plus I effect of only 1 methyl, and here there is nothing stabilizing this methyl carbocation. Dear students, not only the plus I effect of these methyl groups, but also these will exert the carbocation is stabilized by hyperconjugation also, which you will know after some time. Okay. So, this is one of the applications. The next one is about the acidic strength. Now, this is also very interesting. See, here HCOOH. Okay. Here, if it loses acid H plus ion, this acid, if it loses H plus ion, you will get a corresponding formate ion and this H plus ion. Now, if any factor or any group that is attached to this carbonyl carbon, if it gives the electron, it will reduce the acidity. If it takes out the electron, that will increase the acidity, because the electrons are more pulled towards this side if there is a withdrawing one. If they are giving, okay, the polarity decreases and it will become less acidic. So, now we can see here in formic acid, carbonyl carbon, the doubly bonded carbon to oxygen, that is carboxylic carbon, is bonded to hydrogen. But here it is bonded to methyl group, one methyl group. So, it reduces the polarity of OH bond. So, here ethyl group, a better donating one. Then propyl, it may be isopropyl or N-propyl, and this is butyl. So, the electron donating tendency increasing, polarity of this OH bond decreasing, therefore, acidity is also decreasing. You can observe in other examples here. See, phenol, water and ethyl alcohol. Let us compare the acidity. Here, the lone pair of electrons on oxygen are delocalized into the ring. Hydrogen can be expelled as H plus. The resulting phenoxide ion is stabilized by resonance. So, therefore, it is a relatively strong acid. Whereas in water, if it loses H plus, okay, there is no factor stabilizing like the phenoxide ion. And in ethyl alcohol, if it loses H plus, the O minus is, that is here, the polarity is decreased because of the electron donating capacity or because of the electron releasing nature of ethyl group. Actually, the polarity of OH is decreased, where here it is increased because the electrons are being taken into the ring. Here it is decreased because they are given here. The polarity is getting decreased. So, therefore, we can say that phenol is more acidic than water, and water in turn is more acidic than ethyl alcohol. Okay. Now, the next application we can also see here, methyl alcohol is more acidic than ethyl alcohol, followed by isopropyl alcohol and then tertiary butyl alcohol. This can be explained on the fact that here CH3OH, only one methyl group is giving the electrons by plus I effect. The polarity is not that much reduced. As you move down from left to right, as the bulkiness of the alkyl group is increasing, the magnitude of plus I is also increasing. Thereby, the polarity of this OH bond is decreasing. Thereby, acidity is also decreasing. The next one is about, the relative stabilities of carbocations. Here, please understand this point. This is a very important equation. Energy or charge stability. This is one point. This is reflected in another way. Stability of carbocation, if there is a minus effect is pronounced, stability will be less. If the plus I effect is pronounced, stability will be more. So, you can see here, these are here plus I effect due to 3 methyl groups. So, more magnitude, therefore, it is highly stable. Plus I effect due to 2 methyl groups, plus I effect due to only 1 methyl group. So, therefore, the stability of different carbocations is directly proportional to the plus I effect and inversely proportional to the minus I effect. Okay. The other one is about dipole moment. Here, this is an interesting order. Here, we can see the order of dipole moments. We can see the highest dipole moment for methyl chloride, not for methyl fluoride. Though fluorine is more electronegative, highest dipole moment is observed in methyl chloride, because you know that the mu is equal to ED. The product value is higher for methyl chloride. So, it has got higher dipole moment. So, this is the order. Iodine is being very less electronegative, least dipole moment, little higher, methyl bromide, and then methyl fluoride, and the highest is the methyl chloride. So this is also a reflection of inductive effect, that is polarization of CX bond. Okay. So these are the different applications of dipole moment. Okay, dear. The next application is about relative acidic strength of different compounds. Here you can see different carboxylic acids were given, and also phenol, water, and ethyl alcohol. Here if you observe, in formic acid, okay, by the ionization you will get formate ion plus H plus. Now here the hydrogen attached to this carbon is not electron donating or not electron withdrawing. But when you consider in the case of acetic acid, okay, you get acetate ion and H plus ion. This methyl group is electron donating, thereby it is decreasing the negative charge. In turn, we can say that the polarity of the OH bond is decreased, therefore, this ionization is not as easy or as much as in the case of formic acid. Now, when we come to this propanoic acid, because of the further better donating capacity, the polarity of OH bond is further reduced, and as we move from left to right, the polarity of the OH bond decreases, therefore, relative acidic strength decreases. In another set of examples, we can see phenol. Here, the lone pair of electrons on oxygen can be delocalized into the phenyl ring. The OH bond is polar, H plus can be liberated. Therefore, phenol is relatively better acid, okay, compared to other two. Whereas, in water, there is no factor stabilizing the hydroxide ion compared to the phenoxide ion, and in ethyl alcohol, here ethyl group is actually electron donating and reduces the polarity of OH bond. So, therefore, these are the relative orders of acidic strengths of these two sets of molecules. Okay. Next, here another comparison is given between methyl alcohol, ethyl alcohol, isopropyl alcohol, and tertiary butyl alcohol. Here the reduction of polarity of the OH bond is least, because only one methyl group is donating the electrons by plus I effect. But here ethyl group a better donating, isopropyl further better donating, and tertiary butyl has got relatively higher electron donating capacity, thereby decreasing the polarity of the OH bond to a greater extent, thereby the methyl alcohol is relatively a stronger acid. Okay. The next one is about the stability of different carbocations. Here the stability of carbocations here is inversely proportional to the minus I effect and directly proportional to the plus I effect. So, here you can see in a tertiary butyl carbocation, because of the plus I effect of 3 methyl groups, it is highly stable, whereas in isopropyl group, as there are only 2 methyl groups, the stability is little less. Then in ethyl carbocation, only one methyl group is exerting the plus I effect, therefore, it is still less stable, and we can also put here methyl group, this is further less stable, because there is no factor stabilizing that. Here we should also keep one more point in our mind, that not only the plus I effect of methyl groups, here hyperconjugation is also another factor that is responsible for the stability of these ions, which we will discuss after some time. Okay. Next is the after the relative stabilities of carbocation, okay, about the dipole moment. See here we can see the different methyl halides, methyl iodide, methyl bromide, fluoride and chloride. Though fluorine is more electronegative than chlorine, but the dipole moment of methyl chloride is more, because you know that dipole moment is equal to the product of, that is mu is equal to E d, the product of the charge developed into the distance between the two atoms. Here because of the distance is being more, the overall value mu value is higher for methyl chloride. So, here the electron withdrawing capacity, that is the minus I effect of the halogen is the factor. So, here iodine is least electronegative, bromine is little better, fluorine is most, but the distance is less, therefore, it is coming in the second place, and here methyl chloride is having the highest dipole moment. Okay. Next, another interesting effect, that is electromeric effect. It is a temporary effect. There are two types of electromeric effects. One is positive electromeric effect. In this effect, what happens? Here in this effect, the pi electrons of the multiple bond are transferred to that atom which gets bonded to the attacking reagent. You observe this equation. It is a compound with multiple bonds. Okay. Now, it is attacking reagent. Now, what is happening? See, here you can observe the pi electrons transferred to that atom which is bonded to the attacking reagent. So, the pi electrons are transferred to that atom which is bonded to the attacking reagent. This is plus E effect. There is one more effect, that is minus E effect. In this effect, pi electrons of the multiple bond are transferred to that atom which is not bonded to the attacking reagent. Okay. So, you can see this. See, this is a compound containing multiple bonds, this is attacking reagent, polarization. Now, the attacking reagent will attack or bond to other carbon where the electrons are not polarized. So, you can clearly see here that the polarization is onto other one carbon, attacking reagent is bonded to the next carbon. So, again I am reading out, in this effect pi electrons of the multiple bond are transferred to that atom to which the attacking reagent is not bonded. So, the electrons are transferred to this atom and the reagent is bonded to other carbon atom. So, this is nothing but minus E effect. The next electron migration effect is mesomeric effect and resonance effect. Mesomeric effect is nothing but displacement of electron pair which is caused by the adjacent atom or group of atoms, that is a functional group, whereas resonance effect is nothing but interaction of lone pair of electrons with adjacent double bond in a molecule. Okay. So, mesomeric effect is concerned with the stabilization of the molecule, whereas resonance is related to the structure of the molecule. Mesomeric effect has no effect on polarity, while resonance causes polarity in the molecule. Okay. There are two types of effects, mesomeric effects, one is plus M effect and other is the minus M effect. In the plus M effect, electrons are given. So, this is vinyl chloride, the lone pair, one of the lone pairs of electrons on halogen, that is the chlorine, are given. So, again you can see the displacement in the adjacent double bond, you will get the a structure like this. The back polarization of the electron, the negative charge in between the two carbon atoms, and the polarization of double bond onto the halogen will give the original structure. Similarly, in the minus M effect, okay, can observe here, this is propanol, electrons are taken out, that is withdrawn. So, the electrons are coming out, again here we can see the pulling of coming electron movement between the C2 and C3 to C1 and C2. Okay. So, you are getting this intermediate with this positive charge on third carbon and negative charge on oxygen, the back polarization would result in the original structure. So, electrons are taken out, minus M effect. Okay. You can also observe in aromatic systems, minus M effect in benzaldehyde, electrons are withdrawn, these are the resonant structures for the minus M effect in benzaldehyde, and we can also see the plus M effect in allene, electrons are given. So, these are the various resonance structures, okay, we can observe due to the plus M effect of amino group in aniline. Okay. Now, here these are the different groups which exert plus M effect and minus M effect. These are the orders, these are very important in determining certain properties of the molecules like acidity or basicity. Okay. Next. So, this is an interesting comparison here, phenol with a pKa value of 10, okay, and this side nitrophenols, the other side methylphenols are given. So, here we can see that pKa values of nitrophenols is less, means Ka is more, means they are nitrophenols are stronger acids when nitrophenols are stronger acids when compared to phenol. Why like that? Because nitro groups exert minus M effect. They increase polarity of OH bond. Therefore, nitrophenols are more acidic than phenol. That can be reflected in the pKa values. Okay. Further, paranitrophenol has got a lower pKa value, that means higher Ka value, followed by orthonitrophenol, and the effect is not that pronounced in the case of metanitrophenol. Here methylphenols, these exert plus M effect. So, here the acidity values or pKa values are comparable with that of phenol. Okay. There is a slight difference, because they are exerting plus M effect, they are not increasing the polarity of OH bond, therefore, they are not that acidic, and the acidity is the acidic strength is comparable to that of the phenol. Okay. The next one, here the comparison of basic strength of different compounds here. Here we have aniline, okay, aniline, benzylamine, methyl aniline we have. So, here the basic strength compound 2 is more basic. See, the basic strength basically depends upon the availability of electron pair for donation. Okay. So, here in benzylamine, the electron pair is available for donation, whereas in the case of aniline, these are delocalized into the ring, and here also there is a delocalization into the ring, but slight increase in electron density due to the plus I effect of methyl group. Therefore, the order is benzylamine followed by methylaniline and then aniline. Okay. We can have the order comparison of basic strength of different amines in the gas phase. Okay. So, here a tertiary amine nitrogen that is bonded to 3 alkyl groups, and a secondary amine, okay, and primary amine and ammonia. Here, because of the plus I effect of 3 alkyl groups, the electron density on tertiary nitrogen is more, therefore, it is having highest strength compared to the remaining amines. Here there are only 2 alkyl groups, they are giving the electrons through plus I effect, and here there is only 1 alkyl group giving the electrons, giving the electrons through plus I effect. So, in the gaseous phase this is the order. Okay. But when we consider in the aqueous phase, the order is changing. See, this is the order with ethylamines and this is the order with different methyl substituted amines. There are 3 factors that are responsible for these orders. One is plus I effect, the other one is solvation effect, and the third one is steric factors. Third one is the steric factors. Because of these 3 factors, the orders of ethyl substituted amines, ethyl and methyl substituted amines is given, has come like this. Okay. Next, now we have the comparison basic strength of aniline and pyrrole. Here in the case of aniline, these electrons are available for donation, maybe they are delocalized, but still they are available to some extent, whereas the electrons on this nitrogen, they are involved in the aromatic sextet. So, they are in the delocalization into the ring, they are not available. So, therefore, aniline is more basic than pyrrole. Okay. The next electron migration effect is hyperconjugation. So, in hyperconjugation, it is there takes place delocalization between, see, these are the is a sigma bond, this is alpha carbon. Now, these electrons will overlap, this bond will overlap with vacant p orbital that is present on this carbocation. Okay. Here the overlap is taking place, as a result we are getting this structure. Now, because these electrons moved here, there is no bond. So, this is also called as no bond resonance. So, with one sigma bond we have shown the structure like this, and we can show like this with these 2 hydrogens and also with the remaining 6 hydrogens. Totally 9 such structures are possible, which we call them as 9 hyperconjugative structures. More the number of hyperconjugative structures, more will be the stability. Okay. Now, let us see about the stability of free radicals. Here this is sp2 carbon, these are the 3 alpha hydrogens, 2 more and 2 more. Totally there are 7 alpha hydrogens, and in this free radical this is sp2 carbon, 2 alpha hydrogens and 2 more. So, totally there are only 4 alpha hydrogens, and in this compound, okay, in this free radical, this is the free radical sp2 carbon, it has got only 1 alpha hydrogen. So, therefore, this is the least stable. So, therefore, the order of stability is the first one is more stable than second, and which is in turn more stable than the third one. Okay. Now, here electron donating power of different alkyl groups attached to benzene ring. See here, to the benzene ring, if methyl group is attached, these 3 hydrogens can participate in hyperconjugation. In the case of ethyl, only 2, isopropyl only 1, tertiary butyl nil. So, the electron donating power is also in the same order. And here the stability of carbocations also has been presented. You can see this is the sp2 carbon, third degree carbon, okay, tertiary carbocation. Now, there are 3 plus 2 plus 2, total 7 alpha hydrogens here, okay. 7 alpha hydrogens are present. In this compound you can see 1 alpha hydrogen, 2 more. So, there are in the secondary carbocation here there are only 3 alpha hydrogens here, 7 alpha hydrogens, and in this one there is only 1 alpha hydrogen. So, therefore, the order is tertiary carbocation is more stable than the secondary carbocation, which in turn more stable than the primary carbocation. Okay. The next one is again regarding the benzyl carbocation stability. Now, such of those groups which can quench the positive charge will stabilize the carbocation, which will withdraw the electron will not stabilize the carbocation. Now, you see here nitro group is electron withdrawing, chloro group, chlorine atom here is electron withdrawing due to inductive effect, but also electron donating due to mesomeric effect, and methyl groups due to plus I effect, and methoxy due to plus M effect. So, here the quenching of positive charge is more by methoxy group, therefore, compound 4 is more stable. Next is the compound 3 where methyl group is donating the electrons. Next is compound 2, okay. Because of the mesomeric effect, though it is withdrawing, because of the mesomeric effect there is some quenching of positive charge, and nitro group is withdrawing the electrons, there is no question of quenching, therefore, that is the least stable carbocation. Okay. Next, here the acidity, the strength of acidic nature or the about the acidic character of various benzoic acids, substituted benzoic acids has been presented here. So, now such of those groups which increase polarity of this OH bond are more acidic. Which will increase the polarity? Those groups which will withdraw the electrons will increase the polarity. So, here nitro group has got strong tendency to withdraw, therefore, it is most acidic, followed by chlorine. Okay. Though it is withdrawing to some extent, it is quenching, but it has got the because of this minus I effect, it is also increasing the polarity to some extent, but not as much as nitro group. Okay. So, this is the first is the this one, second is the parachlorobenzoic acid. In benzoic acid is there is no quenching, I mean there is no group withdrawing or there is no group giving. So, nothing is there, no giving or no taking, no withdrawing. So, therefore, it is in the third position. Now, here between methyl and hydroxy, okay, here hydroxy group is OH, that is oxygen atom is giving the electrons through mesomeric effect, which is relatively more stronger compared to the plus I effect. So, therefore, the decrease, there will be more decrease in the polarity. Therefore, the compound 5 is least basic, that is para-hydroxybenzoic acid is least basic. Okay. So, this is the order of relative acidic strength of different substituted benzoic acids. Okay. Next is related to the basic strength of different amines. Now, regarding the basic strength of amines, the group which enhances the electron density on nitrogen, that compound will be more basic. Now, let us see the different groups. Here nitro group is withdrawing group. So, it is decreasing the electron density on nitrogen. So, therefore, this is the least basic, whereas methoxy group, the oxygen atom, the electrons are given through mesomeric effect, which is a stronger effect. Okay. So, therefore, the electron density on nitrogen will be more. So, therefore, this is most acidic, most basic, relatively it is most basic, okay, followed by methyl group and then chloro group, that can be observed here. Okay. Next one is related to the stability of alkanes, a very important one related to stability of alkanes. Now, here you consider 2,3-dimethyl butadiene, sp2 carbons, there are 4 alpha carbons having 12 alpha hydrogens. Therefore, it is having, it can exhibit 12 hyperconjugative structures. When we come to the next compound, this is 2-methyl butadiene, there are only 3 alpha carbons and 9 alpha hydrogens. In butadiene, there are only 6 alpha hydrogens, and propene there are 3 alpha hydrogens, ethene there are no alpha hydrogens. So, you can see more the number of alpha hydrogens, most stable and least heat of hydrogenation, and here you can see least stable, highest heat of hydrogenation. So, heat of hydrogenation is inversely proportional to the stability of alkanes. This fact is based on hyperconjugation. Okay. Now, I am going to discuss some questions that were asked in the previous NEETs. Okay. This is the first question, NEET 2023 Manipur. Okay. Which among the following is least basic? Okay. We already discussed that the basicity of a compound depends, that is the basic strength of the compound depends upon availability of lone pair of electrons on that. Better or more is the electron density on the nitrogen, more will be the basic nature. If you observe the 4 options here, in the second option we can find a carbocation, an electron deficient species. The lone pair of electrons on this nitrogen will be completely involved in quenching the positive charge. Therefore, these are not available or rather least available for donation. Therefore, compound option 2 is the right option. This is least basic species or option among the given options. Okay. Next, here they gave 2 statements. An organic compound, when inductive in an organic compound, when inductive and electromeric effects operate in the opposite direction, the inductive effect predominates. No, it is the electromeric effect that predominates, not inductive effect. So, statement 1 is wrong. Hyperconjugation is observed in xylene. Yes, xylene is nothing but CH3. This is orthoxylene, or you can write metaxylene and paraxylene. So, here he gave 4 options. So, second is correct. So, statement 1 is false, statement 2 is correct. So, the correct option is second is the correct option. Okay. Next, see again he gave 2 options, 2 statements. Statement 1, that is assertion, chlorine is an electron withdrawing group, but it is orthoparadirecting in electrophilic aromatic substitution. Correct. Next, inductive effect of chlorine destabilizes the intermediate carbocation formed during the electrophilic substitution. However, due to more pronounced resonance effect, the halogen stabilizes carbocation at ortho and para positions. Correct. Both are correct, and reason is the correct explanation of A. So, option 2 is the right answer for this question. Okay. Next, so he gave 4 carbocations and is asking which of the following is more stable. So, again the concept of resonance, we have to apply the concept of resonance here. Here this can be stabilized by the resonance of adjacent double bond here and one more double bond here, but whereas in other options that is not possible. So, here we can say option 1 is the right option. Okay. More stabilized due to resonance of two adjacent double bonds. Okay. Next, see, this is a simple question. Tertiary butyl carbocation is more stable than the secondary butyl carbocation because of hyperconjugation. Okay. It is the hyperconjugation. Tertiary butyl carbocation has got 9 alpha hydrogens, therefore, it is the most stable carbocation. Okay. So, option 1 is the right option. The next question is, so he gave 4 carbocations and is asking us to find out the more stable carbocation among the given compounds, okay, or given carbocations. So, this is a here this is the carbocation having 2 alpha hydrogens, and in this case you can draw the structure C H CH3 plus C CH3 CH3 CH3. There are only 3 alpha hydrogens in this compound, in this carbocation, 3 alpha hydrogens, and here we can see the 4 alpha hydrogens and here 5 alpha hydrogens. So, therefore, option 4 5 alpha hydrogens, therefore, option 4 is correct. Okay. Next one, which of the following carbocations is expected to be most stable? So, this is related to electrophilic aromatic substitution. Okay. Here observe the 4 intermediates, correct option is the first option, why I will explain. Okay. Observe the resonance structures of nitrobenzene. You can observe positive charge at ortho, para and ortho positions, that is less electron density at ortho and para positions, more electron density at meta position. Therefore, when the electrophile attacks at meta position, this is the intermediate that is formed. Therefore, option 1 is correct. Okay. Next, which of the following is correct with respect to minus I effect of the substituents? Okay. He gave 4 options, we already know the order. Okay. So, according to this order of minus I effect, fluorine is highest, next is alkoxy and the least is amino. So, third option is the right option. Next question, which of the following is the most correct electron displacement for a nucleophilic reaction to take place? So, first option is the correct option, this is the nucleophile attacking on this carbon, the displacement will take place in this direction. So, first option is the right option. Okay. Consider the following 3 free radicals he gave, in which of them hyperconjugation occurs. Okay. So, this is compound 1 or free radical 1, no alpha hydrogen, no hyperconjugation. Second also no alpha hydrogen, no hyperconjugation. In the third free radical, here there is alpha hydrogen, therefore, hyperconjugation will occur. So, first option, in third compound there will be hyperconjugation. Okay. Next, in which of the following compounds the CCl bond ionization shall give most stable carbonium ion? They give actually carbocation they should call. Okay. So, now 4 options he gave and it is very easy to give the answer, that is the fourth option, because by the ionization of compound 4, the CCl bond, we will get tertiary butyl carbocation, which is most stable, containing 9 alpha hydrogen. Here if this ionizes, there will be 6 alpha hydrogens. Here the electron withdrawing group destabilizes the carbocation, and of course, here also you are getting a benzyl carbocation. So, tertiary butyl carbocation is most stable among the 4 options. Okay. Next, arrange the following in the increasing order of stability. So, again he gave different carbocations. Okay. Now, the only thing is that you have to find the number of alpha hydrogens present in each of them, and then that will be the right option. So, here if you observe them, in the first option is the right option, because here B is having highest stability, that is tertiary butyl carbocation, followed by A, that is in this you can find 8 hyperconjugate to stabilization structures here, and then followed by C isopropyl, then ethyl and then methyl. So, it is a very simple question which is based on the number of alpha hydrogens present in a different carbocations. Okay. There is a similar question that is regarding carbocations and this is regarding free radicals. Again, homolytic fission of the following alkanes, they will form free radicals. So, you have to arrange them in the increasing order of their stability. Okay. Here we can see that answer 2 is the right answer. Why? Just is a simple question again. So, here you can see the again tertiary butyl free radical, okay, containing 9 alpha hydrogens, here 8 alpha hydrogens, 6 alpha hydrogens, 3, okay, like that. This is the correct order where the options are based on the stability of free radicals, which in turn reflecting on the hyperconjugation mechanism. Okay.